Deep beneath the streets of London, in caverns carved by human hands over a century ago, archaeologists recently made a discovery that should have been impossible. They found a perfectly preserved Roman coin from the year 3087 AD, sitting next to a shard of pottery that carbon dating placed at over 2,000 years old. But here's what made them pause. The pottery contained microscopic traces of aluminium oxide, a compound that Romans couldn't have produced with their technology. Now, there's a perfectly reasonable explanation for this anomaly. Contamination from modern sources, unusual mineral deposits, errors in dating techniques. But for just a moment, these scientists had to confront an unsettling question that goes to the very heart of how we understand our planet's history. What if everything we think we know about who came before us is wrong? What if we aren't the first intelligent species to develop technology on this planet? What if, buried beneath millions of years of rock and sediment, lie the traces of civilizations so ancient that we've never even imagined they could exist? This isn't the plot of a science fiction movie. This is a serious scientific hypothesis that's forcing us to reconsider one of our most fundamental assumptions about Earth's history. It's called the Silurian hypothesis, and it suggests that industrial civilizations might have existed on our planet millions of years before the first human ever walked upright. Today, we're going to take you on a journey through deep time, through the cutting edge of astrobiology and geology, and into one of the most mind-bending questions science has ever seriously asked. By the time we're finished, you'll never look at a rock formation, a fossil, or even your own backyard quite the same way again. Let's start with a thought experiment that will help us understand just how recent we really are in the grand story of Earth. Imagine if the entire history of our planet were compressed into a single year, starting on January 1st and ending on December 31st. Earth forms on January 1st. The first simple life appears sometime in March. Complex cells don't show up until August. The first animals emerge in November. Dinosaurs rule the Earth from mid-December until December 20th. And modern humans, we appear on December 31st at 11:58 p.m. Our entire recorded history, from the invention of writing to the present day, represents the last few seconds before midnight. This perspective is crucial for understanding why the Silurian hypothesis is even possible. We tend to think of human history as vast and all-encompassing, but in geological terms, our entire species is a recent blip. Industrial civilization, the kind that could leave detectable traces in rock layers, has existed for less than 300 years. That's not even measurable on a geological timescale. Now here's where things get interesting. During those billions of years before humans appeared, life on Earth wasn't static. Evolution was constantly experimenting with new forms, new capabilities, new ways of interacting with the environment. We know that complex brains evolved multiple times independently. Octopuses, with their remarkably sophisticated problem-solving abilities, diverged from our evolutionary line over 500 million years ago. Their intelligence evolved completely separately from ours. Dolphins developed complex social structures and communication systems. Crows use tools and pass knowledge between generations. Even some insects display planning behaviors that suggest sophisticated mental processing. Intelligence, it turns out, is not nearly as rare as we once believed. So, if intelligence has evolved multiple times in just the short period that complex life has existed, why do we assume that technological intelligence has evolved only once? This assumption, that humans represent the first and only time that intelligence has reached the level of tool-making and environmental manipulation, is what the Silurian hypothesis directly challenges. But before we dive deeper into this possibility, we need to understand something fundamental about how the Earth preserves its history, and more importantly, how much of that history might be lost forever. Stand in front of the Great Pyramid of Giza, one of humanity's most enduring monuments. Built over 4,500 years ago, it weighs approximately 6 million tons and was constructed from limestone blocks, each weighing several tons. It seems permanent, eternal, a testament to human achievement that will last forever. Now let's take a journey forward in time. Fast forward 100,000 years. The pyramid is still recognizable, but weathering has rounded its edges. The outer casing stones, already mostly gone today, have completely disappeared. Fast forward 1 million years. The structure is now a rounded hill of rubble, barely distinguishable from natural rock formations. Fast forward 10 million years. The Sahara Desert might now be a lush jungle, or perhaps covered by an ocean, depending on the shifting patterns of continental drift and climate change. The pyramid's limestone blocks have been scattered, dissolved by acid rain, ground down by glaciers that advanced and retreated dozens of times. What remains might be a slightly unusual mineral concentration in the soil, detectable only by sophisticated chemical analysis. This isn't science fiction. This is what happens to everything over geological time. The Rocky Mountains, which seem eternal to us, are babies in geological terms, only about 50 to 80 million years old. The Appalachians, much older at around 300 million years, have been worn down to gentle hills. Mountain ranges twice as old as the Appalachians have been completely erased from the landscape, their existence detectable only through careful analysis of rock chemistry and magnetic signatures. If entire mountain ranges disappear over deep time, what chance do human artifacts have? Let's think about our most durable creations. Nuclear waste, which we worry about lasting for thousands of years, would indeed persist longer than most human artifacts, but even uranium has a half-life. After 10 million years, our most dangerous nuclear waste would have decayed to background levels. What about our cities? New York, London, Tokyo, these massive concentrations of steel, concrete and glass, surely would leave some trace. Well, consider this. Steel rusts. Even stainless steel corrodes over time. Concrete cracks and crumbles. Glass dissolves in slightly acidic water. Over millions of years, even our largest cities would be reduced to anomalous chemical concentrations that might be indistinguishable from natural mineral deposits. This raises a profound question that cuts to the heart of the Silurian hypothesis. If our own civilization, with all its massive infrastructure and technological achievements, would be virtually undetectable after 10 million years, how would we recognize the traces of a civilization that existed 50 million years ago, or 100 million years ago? Most people think the fossil record is like a detailed history book of life on Earth. They imagine that if a species existed, especially if it was numerous or important, we would have fossils of it. This is a fundamental misunderstanding of how fossilization actually works, and it's crucial to understanding why the Silurian hypothesis is even plausible. Fossilization is an extraordinarily rare event. For an organism to become fossilized, it needs to die in exactly the right place, under exactly the right conditions. It needs to be buried quickly in sediment, protected from scavengers and bacteria, and then subjected to the right chemical processes over millions of years. The vast majority of organisms that have ever lived left no trace whatsoever. Consider this sobering fact. We have fossils representing less than 1% of all species that have ever existed.
Let's make a change here. And for most species we do have fossils of, we have only a handful of specimens. The entire fossil record of Tyrannosaurus rex, one of the most famous dinosaurs, consists of fewer than 50 individual specimens, and T-Rex lived for about 2 million years and was probably relatively numerous. Now think about this in terms of potential ancient technological species. How many individual humans would you expect to be preserved as fossils from our current era? We bury our dead in ways that don't promote fossilization. We cremate many bodies, destroying any chance of preservation. We die in hospitals and homes, not in sedimentary environments. Future paleontologists might have tremendous difficulty finding fossil evidence that humans ever existed, even though we currently number in the billions. But surely technological artifacts would be preserved, right? Our tools, our machines, our infrastructure. Here's where the challenge becomes even more daunting. Most of our technology is made from materials that don't preserve well over geological time. Plastics break down, metals corrode, electronics contain materials that are chemically unstable over long periods. The few materials that might survive millions of years are precisely the ones that would be hardest to distinguish from natural formations. Ceramics can last, but natural clay deposits can look very similar to fired pottery. Some glass formulations are extremely durable, but volcanic glass occurs naturally and has similar properties. Even more challenging is the question of context. Imagine a future paleontologist finding a single ceramic fragment that was clearly artificial. Without context, without associated organic remains to provide dates, without other technological artifacts nearby, how would they interpret it? Would they assume it came from an unknown technological civilization, or would they more likely conclude it was contamination from a more recent period? This isn't just theoretical speculation. Archaeologists regularly encounter artifacts that are difficult to interpret, objects that seem too advanced for their supposed age, materials that don't match the technological capabilities we assume for certain time periods, anomalous chemical signatures that don't fit our models of ancient life. Most of the time there are reasonable explanations for these anomalies, but the Silurian hypothesis forces us to ask, what if some of these anomalies represent something we've never considered? What if some of them are genuine traces of technological civilizations so ancient that we've never even imagined they could exist? In 2018, two scientists published a paper that would fundamentally change how we think about ancient life on Earth. Gavin Schmidt, a climate scientist at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester, weren't setting out to prove that ancient civilizations existed. They were asking a much more subtle and scientifically rigorous question. If such civilizations had existed, would we be able to detect them? Visual, Schmidt and Frank in their laboratories working with data. The genesis of their collaboration was itself fascinating. Frank had been thinking about the long-term sustainability of technological civilizations, particularly in the context of astrobiology and the search for life on other planets. He was troubled by what seemed like a fundamental gap in our understanding. We know that planets can support life for billions of years, but we also know that technological civilizations can dramatically alter their planetary environments in relatively short time periods. Visual, comparison of Earth's atmosphere before and after industrialization. Narrator. This led Frank to wonder about something that seemed almost unthinkable to most scientists. Could technological civilizations have existed and disappeared on Earth itself, long before humans evolved? When he approached Schmidt, who was an expert in climate modelling and the analysis of ancient climate data, they realised they could approach this question with rigorous scientific methods. Visual, ancient climate data, ice cores, sediment samples. They decided to call their investigation the Silurian hypothesis, referencing the intelligent reptilian species from the British science fiction series Doctor Who. In the show, the Silurians were Earth's original intelligent inhabitants who went into hibernation millions of years ago when they detected an approaching cosmic catastrophe. The fictional Silurians represented exactly the kind of scenario Schmidt and Frank wanted to investigate. What if intelligence had evolved on Earth long before humans? Visual, Doctor Who Silurians alongside real fossil reptiles. Narrator. But Schmidt and Frank weren't interested in speculation or science fiction scenarios. They wanted to develop testable scientific criteria. What signatures would a technological civilization leave in the geological record? What kinds of evidence should we be looking for? And most importantly, what would distinguish artificial signatures from natural phenomena? This approach represents a fundamental shift in how we think about ancient life. Instead of looking for fossils or artifacts, they proposed looking for something much more subtle, but potentially more persistent: the chemical fingerprints that industrial activity leaves in Earth's geological layers. The chemistry of civilization, 38 to 48. Narrator. Every technological civilization leaves chemical signatures in the environment around it. When we burn fossil fuels, we don't just release carbon dioxide into the atmosphere. We release carbon dioxide with a very specific isotopic signature that reflects the ancient biological processes that created those fossil fuels millions of years ago. Visual. Animated carbon atoms showing different isotope ratios. To understand why this matters, we need to think about carbon isotopes. Carbon comes in different varieties or isotopes with slightly different atomic weights. Carbon-12 is the most common, but carbon-13 also occurs naturally. Living organisms preferentially use carbon-12 in their biological processes, so organic matter tends to have a higher ratio of carbon-12 to carbon-13 than inorganic carbon. Visual. Photosynthesis process showing carbon isotope selection. Narrator. When we burn fossil fuels, which are the remains of ancient organic matter, we're releasing this carbon-12 rich carbon dioxide into the atmosphere. This creates a distinctive signature in the isotopic composition of atmospheric carbon that gets preserved in various ways. Ice cores trap ancient atmospheres in bubbles of air. Ocean sediments record the isotopic composition of ancient seawater. Even tree rings can preserve information about the atmospheric chemistry of the years in which they grew. Visual. Ice core drilling, sediment analysis, tree ring examination. But carbon isotopes are just the beginning. Industrial civilizations also alter the ratios of many other elements. When we mine metals, we concentrate materials that were naturally dispersed. When we create alloys, we combine elements in ratios that don't occur in nature. When we produce synthetic chemicals, we create entirely new molecular compounds that have never existed before. Visual, mining operations, metal smelting, chemical manufacturing. Narrator. Consider plastic production.